Okay, it seems that it works, huh? Okay, very good. So yes, I was saying that for all this type of system, you need to design and implement a flow model. So here is an example of flow model where you have pumping wells here, and here this is a source of contamination, and so the different models here try to predict where the contaminant plume would go and what is the risk of contaminant to the wells. Here is another example now in a vertical cross section where you see different types of porous media here with different permeability and the transport of a contaminant to a lake, to a river, and to a well. So this is a typical problem of groundwater flow that needs to be solved. For reservoir modeling, things are similar. Okay. So now I'm going to switch to the board. Oh, just a second. I'm going to connect my iPad to write.
Recording in progress.
Okay. Now you should see my screen. Just a second. Can you hear me well? Okay, it's still good, yes? All right. So now I switched to the board to now go into the details of the basics, fluid mechanics of porous and fractured media that you need to know for this type of applications. I think we have about 1 hour now left for today. So we are going to go through some fundamental concepts and then do an exercise together. All right. So the first thing to start is to understand okay, the different types of rocks that we can find in this subsurface environment. So there are three basic types of rocks. And this you probably have seen in other classes or other lectures already or before. We have sedimentary rocks. So they are typically formed at low pressure and temperature. This is at the more or less at the surface. We have metamorphic rock. They correspond to a change in composition and texture of another rock due to high pressure and temperature. And then we have what is called igneous rocks, which are formed from cooling of a molten magma. So typically granite or basaltic. So for us, this is important to know this. I'm assuming that most of you already know this, but what we are going to learn here is that how this type of rock influence the hydraulic property. How do these different types of formation of rocks influence the hydraulic property that control the reservoir properties? And so, sedimentary, metamorphic, igneous. Within the sedimentary rocks, yeah, there is a question. So I will send you also this handwriting, these slides, but I would advise you to write them as I'm presenting, because I think this will help you. But yes, I will send you also the handwriting in case you've missed something. So on the sedimentary rocks, we have three types also of sedimentary rocks. The clastic, what is called clastic rocks. They are formed from fragments of other rocks. So sediments, like sandstone, for instance. They can be of chemical origin. In that case, they are formed from a precipitation of ions in solution. So typically limestone. And they could be organic. So in that case, they are formed from dead dead microorganisms. Okay. So don't hesitate if you have any question or comments. So these are the main types of rocks that we deal with when we have reservoirs in the subsurface. So now, okay, what maybe you can tell me either in the chat or you with the sound. So for this question here, how do they influence the hydraulic properties? So these different types of structure. So what is for you important in the hydraulic property? What are the parameters that are important and that control the flow or storage in these rocks? Can you either write in the chat or tell with the sound? You know what are the hydraulic parameters that are important? How are they called? So maybe I will ask the group one here. Can you have tell me any idea? It could be if you make a mistake, there is no problem. Can somebody tell me?
Could you repeat the question?
Idea? Yes, so I'm asking what are the hydraulic parameters, so that controls the hydraulic, what are the parameters according to you that control the hydraulics of the reservoirs? Okay, there is here viscosity, permeability. Okay, that's good. Anything else? There is one basic parameter that I think you should know intuitively. So for example, if we compare let's say if we compare on one side a sand, on one side a sand, and the other side the granite. Okay. Porosity. Okay, that's good. So indeed, porosity and permeability are the two key the two key parameters. So here, if we if we go from sand to granite, okay, we have in the sand high porosity. In the granite, we have low porosity. Okay, and in the sand we have high permeability. And in the granite, we have low permeability, generally. Okay. So viscosity is also important in that if you try to inject a highly viscous fluid, what can you take as a viscous fluid? A type of viscous oil, for instance, then you reduce the permeability. So the permeability is, so the fluid is going to have more difficulty to go through a porous media if it's highly viscous. So viscosity is actually affecting the permeability. So we have then that the two main parameters that we want to understand are porosity and permeability. Okay, so
let's start with porosity. Okay, so the definition of porosity. So if we take, let's say, a volume of porous media, volume of rock, at the scale of, let's say, this could be 100 micrometer to 1 millimeter. We have grains of different shapes that depend on the origin of the rock, right? So it could be sediments, or it could be some crystals that have crystallized of a magma, or it could be some precipitate. And around this, you have, in the pore, you have water or other type of fluid like oil, gas. And this goes in all the pore space, like this. Okay. So basically the porosity is how much water you can put, or any other fluid, into a given volume of rock. So the definition is the porosity, usually we use phi, is the pore volume, so this blue volume, divided by the total volume. Okay, so typical values of porosity are the following. So maybe I will let you guess to start. If you take a sand, what would you think the porosity of sand is in general? Can you make some guess in the chat? %? Any other guess? 80%? Any other? So these two are a bit too high, so there is still a chance to win the guess. If you have a guess that is a bit lower than this. $40, yeah. 40 is a bit closer to the answer. So for if we take a pack of spheres, so that you take some spheres, perfect spheres, the porosity has been calculated. So if you take a pack of spheres, okay, you just take a given volume, and you put some sphere in it. Let's say if you arrange the spheres perfectly like this, on top of each other, this porosity here is quite large. It's 48% in idealized porous media made like this of sphere. Now, if you check the spheres, they will tend to arrange in a different way. So they will minimize the space between them, and they will be more like this. Okay, so here we see that we have less space. Okay, and in that case, the porosity is known to be 26% for a perfect arrangement of sphere. So this gives you ideas of typical porosity. But now, if we take measured porosity, in the sand, so this is the question I asked before. Porosity usually goes from 37% to indeed almost 50%. So you are quite right in your estimates. By the way, do you know how porosity can be measured? What is a simple way to measure porosity? No ideas?
Can you repeat the question?
How can you measure porosity of a rock? Archimet principle, not quite. There is something simpler. Any other idea?
First, we can measure the mass of empty rock. Then, if we put this rock into the water, then to put out this rock, then we can measure the new mass of this rock.
Exactly. So what we do is we take the dry rock and then we pour water in it. So the water will invade, or water or another fluid, it will invade the space like this until we cannot put any more water. And then we measure this new mass compared to the dry mass. And then we have the mass of fluid that has been inside. And then we simply deduce the volume of void that was in that rock. So yeah, there is that's really the simplest method. It works, so it will give us the accessible porosity, but not necessarily the total porosity, because some part of the porosity could be a bit inaccessible to in the fluid. So there are other techniques, and maybe I guess like one that was discussed in the chat, like doing some tests of using gas and so on. So here is just the simplest technique that is quite used still. So now if we take, this is just a sand, so like in a beach, but if we take now a sandstone, so a sandstone is a sedimentary rock made of initially of sediments of sand. Because it has been consolidated and compressed, the porosity is much less, and it goes typically from 8 to 38%. And then now if we take concrete, so concrete used for building, right? So obviously this is a very strong material and low porosity. We have typically from 2 to 7% of porosity. And we have two types of porosity. We have the primary porosity. This is formed typically during the deposition or creation of the rock material. And we have secondary porosity. That is formed by subsequent geological processes. So this could be, for instance, fractures or cavities, for example, in karst systems. Okay, so this is for porosity. Porosity is really giving us the amount of fluids that can be stored in a given rock or porous media. But it does not tell us how this fluid can flow. So you could have a lot of porosity and not necessarily a high permeability for the fluid to flow. Okay, so that's why we have a second parameter, that is permeability. Permeability, so the definition is the ability of a rock formation to conduct fluids. Okay, so here related to this concept of permeability, there is a really very important law of fluid dynamics in porous media. It is the most important law. And this is called Darcy's Law. That law was established by a French noble that has some interest into trying to solve engineering problem, called Henri Darcy. And that was
Teacher.
Yeah.
Could you please move your face cam because we can't see definition clearly?
Okay, sorry.
Thank you.
All right. Okay. So it was a French engineer from a long time ago, born in 1803 and died in 1858. And he was trying to solve the problems of water in the city of Dijon in the east of France. And to that, he wanted to be able to predict the flow of water into filters and different types of fountains. And so he wanted to know how much pressure he needed to put on the water for it to flow efficiently. And so he established that famous law of Darcy. So that law is based on this. So he did an experiment. I'm going to draw it here for you, where he had a system like this with a porous media here, so sand typically, connected to 2 levels of water one level here, low level on this side, and higher level on this side. Okay. So one level here that we will call H2, and one level here that we'll call H1. And his question was to what is the flow that goes through the porous media? So obviously, flow of water will go from the high level to the low level. How does this flux of water depends on the difference in the levels? So here we have a given difference delta H between the two levels. If I increase this difference, I will have more flow. But how is it? How is the dependence between the difference and the flow? And so what he showed is that by doing this experiment with very different flow is flow rate, yeah, flow is flow rate exactly. He did this experiment and measured the flow rate for many different differences in height between the two levels, and he found that it was actually proportional, simply linear. So there is a linear relationship between the flow rate and the difference in the level. And so based on this, he established the Darcy's law that states that the flow rate is proportional with a given constant called K to different things. So to the area of porous media. So this is the area here of the porous media exposed to the fluid. It's also proportional to, as we say, the difference in level, delta H, and inversely proportional to the length of the porous media. So this flow rate here is meter cube per second. This difference in level is simply in meter. This length here is in meter. This area here is in meter square. So if we want to have meter square per second for the flow rate, this parameter, this parameter needs to be in meters per second. So meters per second times meter square is meter cube per second. There's no unit because it's meter divided by meter. So we have then this coefficient here is called the hydraulic conductivity. In meters per second. We will see how it is related to another parameter called permeability. Okay, so this is the most important parameter in porous media. And it is also the most variable parameter in porous media. So it's extremely variable. We will see that. And that is often a major cause of difficulty to manage these subsurface systems. Okay, so the typical, let's put some number on it for you to have a ideas of orders of magnitude. So I'm going to take here a scale and consider different types of porous media. So the going from the less permeable to the most permeable. So the less permeable are metamorphic and igneous. So we talked about this before. These rocks either made from molten magma, cooling of molten magma, or from compaction of other rocks. We have shale, that is also quite impermeable. Then clay, sandstone, limestone. So sandstone made from sand, limestone made from precipitation. Then just simple sand, basalt. So basalt is quite permeable because it's molten quickly and has high porosity. We have karst limestone. So this is limestone with cavities, and gravel. Gravel is just simply what you have in the and so the orders of magnitude now you will see is usually variable. So now if we put estimate of permeability in meters per second, hydraulic conductivity. So for the gravel, typically the hydraulic conductivity goes from somewhere like 10 to the minus 2 meters per second to 1 meter per second. It's very, very, very permeable. For karst limestone, it typically goes down to up to 4 orders of magnitude less, from 10 to the minus 6 to 10 to the minus 1. For basalts, we go also down to 2 orders of magnitude and up more or less the same thing. For sand, go again 1 order of magnitude down. For limestone, okay, like this. Sandstone is also a little bit less. Or a little bit is like a factor 10 or 100. And then we go to clay and shale, which are the less permeable. But so here from this image, you notice 2 things: is that there is a huge variability So we are talking about for a factor 10 to the 14. So it's incredibly variable. If you compare this to porosity, for example, you have seen porosity goes to a few percent from few percent to let's say 50%. So it's just a factor 10. Here we have a factor 10 to the 14. So it's really important to think about this. And we also see that within a given type of rock, it can be, sorry, I thought to put one here, similar like this. Even in one type of rock, we have a huge variability. So here we have, for example, 4 to 5 orders of magnitude for each of these types. So this is what makes our life very difficult in the reservoir management. Okay, any questions? Don't hesitate. And this gives you the orders of magnitude. As we said, permeability, hydraulic conductivity is controlling the flow here in this Darcy's law. So this means that for a given pressure difference, so given difference in level is delta H here, we will have huge difference in the flow. So if we can consider either gravel or shale or clay, let's say gravel and clay are often together in let's say in sedimentary settings. We would have between gravel and clay, we can have up to factor 14, 10 to the 14. If you consider this is 1 million of 1 million million, right? It's huge. And this has important implications for managing these systems. Okay, so as we have seen in Darcy's law, here, we have the flow rate is basically how can we change the flow rate? We can change it either through permeability, this permeability, or through the pressure difference, the difference in level. So here in this simple experiment that we have here, sketch above, it's easy to see, okay, what is the level? We have one level here, H1, and another level, H2, and creates the difference. So how do we understand these levels inside the reservoir and aquifer? So here we need to introduce a concept that is also very, very important, called hydraulic head. The hydraulic head is after the permeability, the second most important porous media. And so how do we define this? So basically, if we take, let's take a column, just or a glass of water of a certain size and a certain water level. Okay, so here is a simple system. And so you can see that because of equilibrium of pressure in this glass, the level. So if we take this system, we take a point here and another point here. So these 2 points have different pressure. because the deepest point has more water volume on top of it. Okay, so they have different pressure. And what is their pressure? So let's take a scale here, going from 0 at the bottom to a big H here at the water level. And I have a position Z1 here for this one, and Z2 for this one. So what is the pressure in these two at these 2 points? Any idea from the students? How do I calculate the pressure of these 2 points? Rho GH. Yeah, very good. So this is easy for you. So rho G and H, this little h that you wrote, is going to be the height of water. This height for this one, and this height for this one. Okay. So I'll write it rho G. So it's going to be big H minus Z1 for this one. And this one is rho G, big H minus Z2. Okay. So these are different pressures. But if I connect this column to a given porous media, let's say I connect this here. To a given porous media. The flow going through this is only dependent on the total water column here. So any point, this point or this point, so the P1 or P2, they fill the same water column. They have the same water column. So whatever they have different pressure because they are at different positions in the system in the depths, but they have the same water column, same height in total, and so the flow of water is not dependent on these two pressures, as we have seen with Darcy's law. Is just a function of the big H. So then we define that these 2 points have the same hydraulic head, that is big H. Okay. So big H, if I take these two equations, I can easily show that big H is, if I put this rho G on the other side, right? It's P1 over rho G plus Z1, but it's also P2 over rho G plus Z2. These two are equal. This is big H. And this is called the hydraulic head. And the hydraulic head is in meters. So this is the second most important parameter, as I said, after hydraulic conductivity. And so if we take water, fresh water, in fresh water, we know that 10 meters of water equals 1 bar of pressure. Okay, and this is because, as we see from the definition of hydraulic head, rho G is about 0.1 bar per meter. So if we take P over rho G, if I take 1 bar over 0.1 bar per meter, I have 10 meters of head. Okay, so that's the definition of hydraulic head is just saying this. And so what is important to understand here is that in Darcy's law, there is not the pressure directly here. We are not talking directly about pressure. We talk about, so this thing here is not pressure, is hydraulic head. It's a difference in hydraulic head that counts. Okay, so we have still a few. I think how do we measure the pressure inside the rock? Okay, good question. So typically how we do, if we are, sorry, at the surface like this, how we measure the pressure. So we drill a borehole. And what we will see is that this borehole will be full of water until a point of equilibrium here that is called the piezometric level. Okay, so this piezometric level is actually a measure of the hydraulic head. So it means that the level here inside the piezometric the borehole will equilibrate with the level outside. I can do it in color. That is a result of the distribution of water into the system. Okay, so again here I have if I measure pressure just by a pressure sensor at the bottom, here at this point I will have a high pressure because of all this water column. And if I measure pressure at this point here, sorry, if I measure pressure here at this point, up the point closer to the surface, the pressure is not so large because I just have a small amount of water column on top of it. But in these 2 points, the hydraulic head is the same. Okay, because this is given by my measure of hydraulic head, that is the water, the level of water. And so if I drill another borehole here, I will see that the hydraulic head is lower. Okay, so then I will know from Darcy's law that the flow goes from the high hydraulic head to the low hydraulic head. And I can calculate the flow rate based on Darcy's law if I know the permeability, the hydraulic conductivity, sorry, of the reservoir. So this is really an important concept, and we will next for the next lecture we will do some exercise to understand this better. So to finish, I wanted to because there was a question, somebody mentioned viscosity. So how do we include viscosity in this picture? And so here we have to introduce another parameter. So we talked about hydraulic conductivity. And we will define another. Sorry. Another parameter that is called intrinsic permeability. So because, as we said before, hydraulic conductivity depends on fluid viscosity. So if we try to flow, and Darcy made his experiment with water, but if he would have tried with heavy oil, it would have given similarly a linear relationship with a different permeability. Sorry, hydraulic conductivity. And so to define a parameter independent of viscosity, it was defined the intrinsic permeability like this. Little k here is the viscosity divided. Oh, sorry. Yeah, that's it. Viscosity divided by rho g. So same rho g as before, times the hydraulic conductivity. So it means that the hydraulic conductivity is equal to the intrinsic permeability times rho g divided by viscosity. So indeed, if I increase viscosity, I reduce the hydraulic conductivity. Okay. And so let's have a look at the units of this. As we said, hydraulic conductivity, this is meter per second. Rho g it is per meter square per second squared. Viscosity, this is in kilogram per meter per second. And so if you calculate all this, and there is another unit that is often used in a reservoir is the unit of the Darcy. And so 1 Darcy, 9.8697 centimeters squared. So it's also a unit for intrinsic permeability. Okay, can you repeat the last part? Which part were you asking? About intrinsic permeability? Yeah. So intrinsic permeability is defined as this, with this definition, and intrinsic permeability is independent of viscosity. So it means it's just a property of the porous media, and then if we put different fluids of different viscosity in this to flow through this, will not change the intrinsic permeability, but we will just change the hydraulic conductivity. And so what I said is that this has unit of meter squared here, meter squared, and it can be expressed also in Darcy. It's another unit that converts just by this definition here. So 1 Darcy is 9.8 centimeters squared. So that's just a definition, and you will find sometimes people prefer to talk about permeability in meter square or Darcy, and some others prefer to talk in hydraulic conductivity. Okay, yeah, it's time to finish. So we will continue, I think it's tomorrow. And thanks a lot for your attention. I will send you the notes that I've written today for you.